So, good morning, one and all present here. So, without further delay, I invite all the dignitaries to the dais. Please, all of us, all of you, please take your seats. I invite Director Sir, our foreign experts, Dean RNC Professor M.A. Ahmed, Dean Academic Professor S. Busho, Dean FW Professor Pramod Patwari, Professor B.K. Roy, HOD Dr. B.K. Tiwari. So now we invite all the dignitaries on the dais to please light the diya, uh, start, mark the start of the function. Now I would request our director sir to welcome the guest, the foreign expert for this Gyan course. Thank you, sir. So, good morning, one and all present here. So, it's my privilege to welcome everyone present here to the fifth Gyan course of Electrical Department and the fourth in control topic. The topic of this Gyan course is active control of aerospace structure. It's my honor indeed to welcome our director, sir, Professor Shivaji Bandyopadhyay, who, in spite of his busy schedule, has taken time off to be present here and grace this inaugural ceremony as chief guest of the function. I, on behalf of the entire NIT fraternity, Electrical Engineering Department, heartily welcome Professor Kumar Vikram Singh, Professor of Mechanical and Manufacturing Engineering, Miami University, USA. Professor, it is our honor to have you here with us today as an expert for the course. I welcome Dean Academic, Professor S. Bosho. He has always been a source of inspiration to us in such events. Next, I would like to welcome Dean Research and Consultancy, Professor M.A. Ali Ahmed, to be a part of this august occasion. I welcome Dean Faculty Welfare, Local Coordinator, Gyan, NIT Silchar, Professor P.K. Patwari. I welcome Head of the Department, Dr. P.K. Tiwari. Next, the source of inspiration for control research, Professor B.K. Roy. I welcome you, sir. Then I sincerely welcome, without whom this course has no meaning, the participants. So please accept my heartiest welcome. And this course is possible because you have registered for this course. So thanks for your generosity and the help and your interest for this course. So welcome to the course. I am grateful, thankful to all the participants, outstation participant who has registered for this course. There are few outstation participants. We extend our welcome and we are thankful to you so that you have registered for this course and shown your interest. Now let me quickly introduce the expert for this course. Professor Kumar Vikram Singh is a professor and graduate program director in the Department of Mechanical and Manufacturing Engineering, Miami University, USA. He has received his BE in 1997 from Birla Institute of Technology, Mesra, in mechanical engineering, and he did his PhD in mechanical engineering from Virginia State University in 2003. He joined Miami in 2006 after serving as a postdoctoral research associate for 3 years at Virginia State University. After his bachelor's degree, he was graduate engineer at Hindalco. He has also held rank of visiting assistant professor at LSU in summer 2007. He was summer faculty fellow at Air Force Research Lab USA 2009 to 11, 2013-14, 2016 to 19. He is a visiting senior fellow at University of Liverpool, UK in 2009 and a visiting researcher at Aerospace System Directorate, USA. His research focus is on inverse eigenvalue problem related to multidisciplinary areas of vibration, aeroelastic control, structural health monitoring, rotor dynamics, smart material and composite structures. In particular, his interests are in developing technologies for active control of aerospace structures, rotors, and viscoelastic material, strategies for parameter estimation, design and system identification based on dynamics or vibration data. He is an author, co-author of more than 75 peer-reviewed international journal and conference articles. His research is supported by NSF, USDA, that is the Department of Agriculture, and AFRL and MathWorks grants. He is an associate fellow of American Institute of Aeronautics and Astronautics and a recipient of the Arthur Olson Teaching Excellence Award and Outstanding Researcher Award in the College of Engineering. He is also registered professional engineer, licensee in mechanical in the state of Louisiana. So this is his short uh, achievements and biodata. So I believe the participants who have registered for this course during this 5 to 6 days of the interactions or the lectures, they will really gain a lot of insight into multidisciplinary research. Let me tell you, he is not a control guy directly. He is from mechanical engineering who applies control. So I think for our participant, it will be interesting to know how physics get fused with the practical problem and mathematics and all this. That I had an interaction with him, and he said that I don't prove theorems. I apply mathematics to solve real problems. So I think that's a best platform for our participant to learn from a professional engineer as well as a teacher how to use these theories that we teach in real life problems. He works with Boeing, Lockheed Martin. So he visits their laboratory, then he understands the problem, he tries to use it. That's exactly, he told me, will be his way of teaching here. So trying to shape the minds, young minds, in a practical way, have a balance between a theory and a practical. So I think it will be a wonderful uh, 5 days program. I believe you will enjoy it, and I hope this workshop will be a success. So now I will invite our local GYAN coordinator, uh, Professor Patwari, to say a few words.
Thank you, Dr. Rajiv. Very good morning, respected Professor Bandyopadhyay, the director of the institute, our foreign expert, Professor Kumar Vikram Singh, my other colleagues on the dais, the participants, and especially the outside participants. I heartily welcome all of you in this 17th GYAN course in the institute. So in the second phase, this is the last GYAN program, the approved GYAN program in the institute, and I feel very much proud that the institute has successfully completed 16 programs and the 17th program is on the way. So in this way, we are taking an active role, we are playing an active role in conducting the GYAN course of MHRD. We are very much thankful to the MHRD and National Coordinator IIT Kharagpur to give us the opportunity for conducting these mini GYAN courses. I believe the expectations of the participants will be met in this course, and they will definitely enjoy the program because we have such a multidisciplinary person in the campus and he is conducting the course, and I think the participants from all the backgrounds will definitely get benefited by this program. Thank you all.
Thank you, sir. Now I would request our Dean Academic, Professor Vaishya sir, to say a few words.
A very good morning to all. Honorable Director Professor Bandyopadhyay, our foreign expert Professor Kumar, my colleagues, other colleagues on the dais, my dear participants. After a long gap, we have been conducting this course, and control itself is a interdisciplinary, and this is the ideal case where a professor from mechanical engineering will teach us the control. So definitely it will have more practical orientation, as already coordinator has highlighted it. So I believe this course will definitely be beneficial to all the participants, and the timing is very good. Our classes are going to be started next week, so this week we are free. All the students, those who have registered, they can easily participate, attend the classes without hampering their normal classes. So this is a very good time chosen by the coordinator. Rajiv, this is not his first course on this GYAN course. He has conducted previously some other CAN courses also. So I congratulate him in organizing such event and completing all the events successfully. I wish all the participants, you all are not matured. I believe you will attend the courses very seriously and utilize the opportunity of the expert who is the real expert. As from the biography, it is clear that he is solving more practical oriented problems. So this will definitely be give you a good direction for research in this area. I hope you will carry forward whatever you learn here. You will nurture it and make a good career. Wish you all the best. Thank you.
Thank you, sir. Now I would request Dean R&C, Professor M.A. Ahmed, sir, to say a few words to the participants.
Good morning, respected Director and Assistant Expert for an expert of the course, Professor Kumar, esteemed colleagues, participants. So this is another opportunity to have some interdisciplinary research. So my only objective in this program is to make you aware that from this program have some collaboration with the faculty or an expert, write some project and publish some paper. If required, PhD scholar and MTech student, I will request you please formulate your research topic if you have not done till date from this 5 days discussion. That will be the great achievement for this program. Thank you. Thank you, everyone.
Thank you, sir. I would request our guest, Professor Vikram, to say a few words to the participants as well as to.
Good morning, everyone. Hear me? First, I would like to thank Pandya and IT Essential faculty and especially Rajiv for inviting me for this workshop/course. I am from Ranchi, originally from Ranchi, not that far from here, but the farthest east I have been to in Calcutta. This is the first time I am in Northeast. It's a pleasure to be here. While driving back, I was telling Aniket that after 98, this is my first monsoon in India. And, it feels like home. So, as you know that I'm a mechanical engineer, and I'm very much excited to work with electrical engineers here. I do work as the MSTC at AFRL, which is an interdisciplinary group, where people from different departments come together and try to solve a problem. My last 10 years of experience in this area has taught me that zero-elastic control, which will be the focus of this active control strategy which I've been talking, is not only interdisciplinary, it's also very difficult problem to solve mathematically, because there are a lot of complexity involved in this particular problem. You can just think of the scale of the aerospace structure. You have to model it, so modeling is a challenge. And then on top of that, you need to understand the interaction between the structures, interaction between the structures and fluids, which is the aerospace engineers who are expert in those areas, then control people. There are a lot of experts in control in this college. So my hope is that after this workshop, you have a better feeling about understanding of what kind of models people use, what is the state of the art. Hopefully, I will be able to teach you one or two new tools which can become a basis for further investigation. And I want it to be a give and take opportunity. It's not that just I am just talking and you guys are listening. I want it to be interactive. Let's have some more discussion, try to understand it better. A lot of time I learn from my own students, so it will be great. I'm looking forward to the workshop. And I hope at the end of the workshop, we'll take some ideas and nurture it for your research. The last thing I just want to say that with changing technology, the only advice I would give all the students that learn, have a habit of lifelong learning, because things will change. In the last 10 years, we have seen a lot of changes in technology, and it's changing fast. The best thing is you can do that, prepare yourself to learn new things every day. With that, I'm looking forward for the course, and thank you once again.
Thank you, Professor Vikram. Now I would like to invite our director, sir, to say a few words.
Very good morning to all the participants, my colleagues here, and obviously Professor Singh. Instead of calling him a foreign expert, say he's a subject expert, mechanical engineer, and then turned into a control area applications. So he is our own PIP. Now, just before coming here, so Professor Singh and with Rajiv, we are having a discussion in my chamber. So basically, the thing is like this. That is why we were late. Otherwise, we would have started the program right at the time. Is that say how to take this relationship forward? Because say Kumar coming here and spending his 7 or 10 days here, and so that is basically based on an earlier relation that started with Rajiv long back, some joint research activities. That is what we call as the confidence building measure between two researchers, academicians, and that later transforms into an institute level confidence building. So that second phase we have reached. And the next phase with Professor Singh, because he is so young, so I'll prefer to call him as Kumarji. So with him, so we were discussing how to take the relationship forward. And so similar kind of thing in the last June visit to 3 US universities. I visited PSU, Pennsylvania State University, Carnegie Mellon, and University of Iowa. So with University of Iowa, we have already initiated the process of having a MOU, Memorandum of Understanding, or similar kind of thing. So we have just initiated that discussion, and maybe during his stay here, we'll take it to the next level. So what that MOU or what the target that we are setting, what it is basically like that. It is not that there will be a lot of financial funding and etc. But it is basically cementing the mutual trust that the two institutes, two universities have among themselves. Each one knows that there is a huge research and academic personnel present in the other institute. So to start with, maybe in the control area, but in other areas as well. And why this becomes necessary, say right from the BTech to the faculty level, this kind of understanding that becomes the pinnacle of these relationships. For example, at the BTech level, there is a SN Bose scholarship, and in order to for a student to apply that, they need the approval or an acceptance from a US university. So for that, there are a lot of applications that goes to a US professor. So out of that, how to select? So the relationship or where we have the MOU that actually comes into place. So that is one point for the BTech. Similarly, for a BTech student, if they wants to pursue their MS or their PhD, or our MS students, master students, they pursue their PhD there. So a lot of applications again go to the that is the students do to the foreign universities. Sometimes say 700 to 800 applications. Then how to select? Because everything there is no interview, so it is based on the recommendations, and at the institute level a relationship that is set up. So the decision is basically based on that one, and obviously the performance and other issues, research activities, H index, and all these things come up. But when there is a strong relationship at the research level, so those things are actually quite natural to combine. For the faculties also, that is why, but the possibilities for a joint research, possibilities for say visit to the research laboratories at the other place. Not only that our people will be visiting USA laboratories, but at the same time the faculties from that institute. So they can also visit our laboratory. We'll have to make it ourselves to that level. So that becomes quite a challenge. But again, that is basically the takeaway from these kind of courses. So similar to the other GAN courses from which say we are maturing that to a future relationship and cementing that. So this is also our wish, and I do believe that during the course of this GAN course, GAN program, so with Professor Kumar Singh, and so we will be arriving at such a situation so that we can take the relationship to the next level. With this wish, I have just one wish for all the participants. That is, let all the participants who are here today, let all of them attend all the sessions of the classes, because what happens at the very beginning, the attendance becomes very high, but as the day progresses, or it becomes quite thin. So let's not be looking like that, because you see that will have an impact on the kind of relationship that with University of Miami and NIT Silchar we are planning to have. If the presence becomes thinner, so obviously our objective will not be achieved. So this is the simple thing in life. So wishing you a very good week after a long gap. That is in the summer, many of you might be re-energizing yourself. Okay, thank you.
Thank you, sir. Now I would like to invite Professor P.K. Roy to say a few words and conclude with vote of thanks too.
Very good. This afternoon, Directors and President of the dais, our foreign expert, my colleague on the dais of the dais, and my dear participants. Just have been entrusted the responsibility of formal vote of thanks. Before that, just one statement. Hope this GAN course will help us think and to do kind of research, kind of collaborative research, cooperative research, what they are doing. Man with mechanical engineering background is doing very active research in all areas of control. I think this is the biggest example of the collaboration that we can have. But unfortunately, despite best effort, we are not getting this thing done here. So this would be a very good message, a messenger, that this should be done, as what Mr. Kumar has said, that we need to, or possibly everywhere we have been saying, the day has come that we need to go for collaborative research. There is no other thought of this one. Now, coming back to my formal responsibilities, I take this opportunity to thank our expert who has accepted our request and has come to share his responsibilities, his knowledge, and I thank him for the approach that he has said. That it's a give and take approach. So therefore, please understand that there is a high possibilities that you all can get something, give something, and there will be a joint win-win situation for all of us. I thank you, sir, for coming here. Next, I thank our director, sir, being busy, and also we were thinking other way that sir might be busy with something else, but as sir has disclosed that he was really thinking how can we have some kind of extension of this particular course with this Miami University. Now, I request all the dean and our HOD to come here and to be present here in this gathering. Finally, my colleagues who are present here and giving support to this GAN course, participants, as Director Sir has said, please do not break the reputation of control electrical engineering department. Department possesses the reputation that our attendance is almost more than 90%. So therefore, since number is very thin this time, I will expect that all of you will definitely remain present. Not because I am saying Director Sir has said, but as your expert sir has said, please try to extract. Please try to extract. And there are many of you who has not formulated your PhD problem also. So therefore, this will be a very good opportunity for you to discuss and see if something can be done in a problem which is very recent and which will give you very good publication, very good citation. And finally, a big thanks to Rajiv conducting one after another GAN course and successfully conducting all of them. By success, there are two parts of the success. One part of the success is what is the result of these 5 days of course. The next part of success is much higher than this. What kind of collaboration that we established with the researcher, with the university of the expert, and what kind of action. As you all know, that at least in one case we have gone ahead, exchanging one of our students to that university, and we are expecting one of their students is coming to our NIT Silchar, right? So therefore, that was a very good extension of this GAN course that was conducted by Rajiv. And finally, the team who are sitting behind, very silently working everything what is being said to them. Big thanks to all those volunteers who are helping us to conduct this particular program, and all the supporting staffs who are here helping in different ways. Thanks to all of you. Thanks.
Thank you, sir. So we come to an end of our inaugural session today. Now, we want that all the participants please introduce yourself from the place itself, just your name and from where you are. Mike?
I think I'm moving because I have got and so good.
So we can have a group photo and then.
Yeah, so I think that is better because time
Okay.
is not on.
So we will.
You are welcome. Let's go.
We can.
हाँ हमारे तो अपन डिस्ट्रिक्ट हाँ उनके सोफाटा था ना we can sit on that one.
तुम बैठो ना
Sir, can I? Ready?
Okay. So we'll take on that.
Sir, do that. We can Mic test love.
Hello.
Good afternoon, everyone. I'm Gaurav Patwari, uh, BTech, third year, Electrical Engineering Department, and I do Session. Thank you.
Good afternoon, everyone. I'm Sandeepan Chakravarti, PhD scholar from Assam, Guwahati.
Good afternoon, everyone. This is Aniket Roy, MTech, Electrical second year.
Fidelity Sahu, Tech Electrical. Good afternoon, everyone. I am Shrishti Jain, MTech Electrical second year. Good afternoon, everyone. Krishna Jyoti, PhD scholar.
Good afternoon, everyone. This is Satyavrat Pradhan from NIT Silchar, Electrical Engineering Department, fourth year.
I am Ankita Sen, a student of NIT Silchar from Upper Assam, Nalur.
I am Pawan Singh from Control System, MTech second year.
Myself, Manojati Theory from Electrical Engineering Department, second year.
Good afternoon, everyone. I am Ravi Kumar, PhD scholar, Electrical Engineering, NIT Silchar.
I am Ariful Masood. I am doing my PhD from Instrumentation Department at NIT.
Good afternoon, everyone. I am teacher in EV, PhD scholar. I am working on optimal control of fraction auto systems.
Good afternoon, everyone. I am Ramasis Banerjee. I am PhD scholar of Electrical Engineering Department.
Good morning, professors. This is Mayank Kumar Gautam, PhD second year Electrical Engineering Department.
Good morning, sir. My name is Rajesh Kumar, and I am doing MTech in Control Systems. Second year.
Good afternoon, everyone. I am Rohit Kumar Maurya. I am from second year NIT Silchar.
Good morning, everyone. I am Prince Kumar. I did my MTech from NIT Silchar, currently working in Jorhat Engineering College.
Good morning. I am Anirudh Nath, PhD scholar, Electrical Engineering.
My name is Tirthankar Chakravarti. I am in MTech second year in Control in Industrial Automation specialization. Thank you.
Good afternoon, everyone. I am Nalini Prasad Mohanty, PhD scholar, NIT Silchar.
Good morning, sir. Myself, Anirban Nanda. I am a second year MTech student of Control System Engineering.
Invite all for IT. So join us for IT. Yeah. Yes, I love the program. Yes.
Okay, good afternoon. So today, at first, I'm going to talk, it's like 45 minutes to an hour. I'm going to talk about the rational background and overview of this particular workshop. And my hope is that I will introduce you a bigger picture why this area is important, challenging. And try to give you a little bit state of the art of the active aeroelastic control. A little bit about myself. I will not take much time. My primary area of research is active and passive vibration control. And in the last 10 years, I have been working in the area of which is called aero-servo-elastic control. This is the focus of this workshop. For last 10 years, I have been working with Air Force Research Lab. It's located in Dayton, Ohio. If you have a little bit history about the aerospace, Dayton is the place where Wright brothers who invented aircraft were born. Rightly so, it has one of the largest Air Force research labs in the world, which is Wright-Patterson Air Force Base, Dayton, Ohio. I work in the Aerospace System Directorate, and they have a multidisciplinary science and technology center. That's where most of my research in this area is concentrated. I have also worked with industry, with General Electrical and Siemens as a senior design project with my undergraduate students in the area of rotor dynamics. What you are seeing is one of the largest aircraft for Boeing 777. These are some of my students. G aircraft engine, the head office is located in Cincinnati, Ohio, which is very close to my university. But my background or my training has been in inverse eigenvalue problem. The idea here is, I say inverse eigenvalue problem, you may think about a mathematical problem. It is. There are a lot of mathematics goes behind this problem. However, practice, what it means that how can you take dynamic data, vibration, eigenvalues, eigenvectors from the measurement and apply it in problem solving, find a system, structural health monitoring. In fact, control naturally is an inverse eigenvalue problem, where you have some poles, where you do pole placement, making an open loop pole closed loop value, and solving for control gain. Essentially, you are doing an inverse eigenvalue. For last 3-4 years, I have been working with developing smart electroactive polymers. One of my colleagues in my department. And I have also developed some of the learning modules, which I will share with you if you are interested, through the support of NSF and my folks. First and foremost, I would like to acknowledge these are my graduate students who has helped me advance my research. I work with them closely. You will see a lot of them have been supported by Air Force, which are the DAXI grant, and they are working in the aerospace companies, which was, and their master's thesis were based on the aerospace project. For example, my first graduate student, Laura, she was the first student I started working, exploring this field of aeroelastic control or active aeroelastic control, and she is working at the Northrop Grumman, which is one of the biggest aircraft companies. In recent years, Charlie has been left corner. She was another AFRL fellow, and she has done. I will show you some of the videos she has done. Basically, 3D printed some of the wings, which will be used for system identification, and it will be used for control implementation. So I have worked with a lot of students, and I really enjoy working with students. I hope this 1 week will not be a one-way street. So please feel free to ask any question you may have. The most, if I don't know that time, I will say I do not know. I will try to find out about your questions. Okay? So feel free to interact with me. Just don't listen. If you don't understand anything, I will try my best to clarify it. Okay, let's talk about the aerospace structures. This is very primitive. I'm just talking the very basic of aerospace design, how airplane flies. So, four fundamental forces in aircraft is lift, weight. You need to generate a lift to balance the weight, and then you have with your engine you have to thrust the aircraft so you can move forward or cruise and overcome any aerodynamic drag it has. Now, if you look at the motion of the aircraft, it's primarily defined in the 6 coordinates. Um, so you have 6 degrees of freedom. This is a typical reference frame for the aircraft. You have the roll axis, yaw axis, and pitch axis, and corresponding to that, corresponding to those directions, you can have U, V, and W translation to those particular directions. So this is in most of the literature when you are going to look at the models of the aircraft. This will be the typical reference frame you'll be working with. People have known the different coordinate system in coordinate, and they will change reference coordinate depending upon the different location on the aircraft structure, which is of the interest. Now, if you look at the aircraft, and I assume most of you have known the aircraft, you have seen a lot of control surfaces, and every control surface has its own purpose. The more major component, you have the fuselage carrying the passenger. This is the main weight of the aircraft. The most important one is your wings. That's what that is designed in a specific shape so that it can generate lift. In terms of control surfaces, the primary ones are the aileron, it changes the roll. You have the rudders at the tail, horizontal tail, that change the yaw. And then you will have the elevators, the pitching. But apart from that, everyone has its own purpose. If you look at the new aircrafts, they have a ringlet at the end. It was to reduce the drag. So in controls, right now what we call fly-by-wire, all the aircrafts, which is defined as the fly-by-wire or flight control system, 50% is, more than 50% is automated, but it can be overwritten by the pilot. They have a lot of redundancy in design, make it a safe flight, and that's the reason you see very few accidents, aircraft accidents. So it's a very mature field. If you think about it, people know how to fly aircraft. They have known for the last few years. What we are looking for that if you want to fly them faster, make it more efficient, nowadays more and more sensor craft, drones, or high-speed fighter jets, when they are being developed, what are the potential challenges? We know how to fly passenger jets, how to make them more efficient. That's the goal of the next generation design of aircraft structures. As you know, control surface, by its definition, it controls the motion of the aircraft with a lot of sense. For example, if you look at the elevator, it controls the pitch. You have the rudder, controls the yaw, and aileron controls the rolling motion of the aircraft, which allows you to ascend, descend, and maneuver with the craft. Now, I'm just going to introduce some of the nomenclature which you will hear subsequently, and I am talking the model. So the key nomenclatures are the horizontal span. If you look at it, call this the horizontal span. That's called the span, the wing in lifting point. This is if it's a rectangular cross section, has a constant value. If it's tapered, then you define it by the mean chord. So the chord is its perpendicular distance to the span, and that's what the mean chord is defined. If you look at the specific cross section of the wing, it will be what is called aileron or This is what we call aileron model. It's a cross section of the wing with a control surface embedded. This portion defines the airfoil of the wing, and this portion defines the control surface. Okay. What are the other ones? We'll call it, this is called the trailing edge of the wing. This is the leading edge of the wing. Whenever we define wing, we will consider it to be a kind of a cantilever beam, which is fixed at the main body. Each wing, depending upon its cross-section material property, is defined by what we call elastic axis. We'll talk about aerodynamic center, and of course, whenever you have a mass, there is a center of mass in the cross-section. These are the term you may see in some of the models. I just wanted to introduce to you. The aspect ratio is very important. If you think about the current aircrafts, don't have a very long wingspan. If we have a very long wingspan, which means a high aspect ratio, we can have a more benefits. But at the same time, it creates a different kind of problem. So we over-design nowadays for safety purposes. We over-design the aircraft and maintain a relatively small aspect. But whatever the passenger aircraft we have, we make it so rigid that for a given aspect ratio, given size of the wing, there is no flexibility. Treat it as a rigid body. And in reality, there is a flexibility in any structure you see around. That's create the problem. That's what we will concentrate in solving. This is a cross section of that wing profile, which I was just talking about, and these are the different important points. For example, aerodynamic center, about which we will calculate the amount of lift and moment, which will define the differential equation. So this is a typical differential equation of an aeroelastic system. You have naturally a second order differential equation coming from the dynamical systems, which will have some inertia component, stiffness component, damping component, which is coming from the structural side. On top of this, and this is, I'm just talking about one cross section 2D model, one slice of the wing. And then it will be subjected to aerodynamic forces. This will interact with the structure. This is the term which will couple with the structure and define what you call its open loop response. Then you can have control, you have to design, and then gust is, I'm just showing you, you can think of the external excitation. So if the aircraft is flying and it is hit by a gust of wind, what will be the response of its mouth? That's turbulence of gust, what you feel in the aircraft when it is excited by those cruise conditions. Now, if you look at the airfoil, the angle of attack, the angle which is made against the direction of the wind, is called angle of attack. Depending upon the angle of attack, the distribution of aerodynamic forces or pressure varies. So, one of the reasons the wing acts like a lifting object because of the shape of its aerofoil. Due to that shape, what happens that the flow goes streamlined on that cross-section shape. And so the flow on top of the airfoil moves faster than the bottom of the airfoil. So it creates less pressure. Then you have a high pressure at the bottom. And the difference of that is lifts the body. That's the fundamental technology principle. Now, that aerodynamic forces changes if the angle of attack changes. So for example, if the angle of attack is, so if the flight is cruising, when you're looking at the airfoil, just think about a wing. Okay? Just flying. So if it's cruising, you have a certain profile of aerodynamic forces that depends on the height, altitude, speed of the vehicle. But if the pilot maneuvers, changes angle of attack, and then the aerodynamic pressure surrounding the aerofoil changes, increase and decrease. So it changes, center of pressure changes with the angle of attack. But if you have to model it, you have to model it for different scenarios. So we define something called aerodynamic center. So what we do, we calculate the lift and moment about a quarter part of the aircraft. This is a good approximation for thin aircraft. And then that aerodynamic center point for a given cross section does not change. About that point, you derive your differential equation of motion and then do the rest of the calculation. Now, any blunt body, when it's surrounded by any kind of a fluid, it will create a stream. And it depends upon how fast the air is flowing over the body and what's its shape. So the flow, the properties of the flow define that how that flow is behaving depends totally upon the shape of the structure, at what fluid it's moving, and at what speed the fluid is moving. That's the very important thing in aerodynamics. And the lift, the definition of lift, or you can also calculate what we call coefficient of drag, depends on these cross sections, depend on these lift coefficient, which is a function of dynamic pressure, which is the density of the fluid at a certain altitude. Remember, the density of air will change as you change your altitude, so that also changes how fast you're going in the plane. Reynolds number, it's related to the fluid property. Mach number, it's the ratio of the vehicle speed with respect to speed of sound. So these are the important coefficients you will see in more simplified model. These are the basic coefficients you will see. The interesting part is what happens that at a certain speed, you will start to see vortices generating outside the plane. And these vortices have specific frequency, and they interact with the structure. Think about a simple lift will be if you, I don't know, as a child, if you are driving, if you are sitting on the bus or going in a car, you take out your hand, just feel the air. You will see after some time the hand will automatically go. You don't have to do anything. It's just due to the lift. If you just move the shape of your hand, it will lift up. So, depending upon the speed, you will have different structure of flow will be developed behind the given structure. So this is the structure for Reynolds number of 30,000. Then we have a turbulent flow where these vortices again breaks up. So you have a different kind of flow profile, which the aerodynamics, the area of aerodynamics talk about how to compute these flow properties. But at the end of the day, what happens? That it creates a natural feedback. You have a structure which is surrounded by airflow, which means it is subjected to pressure. Okay? You have a flexible structure subjected to pressure. So for a given shape, you have a well-defined airflow for which you have a pressure. Due to the pressure, the structure deforms. Due to the deformation, the shape changes, the flow changes. This is a continuous process, and that's a natural feedback loop, which is what we call aeroelastic interaction. You have aerodynamics and elastic structure coupling with each other. One changes, then the other parameter changes, and vice versa. This is a video which will see. This is losing, then start the vortex shading start happening, and that frequency starts to excite this glove body, and then will have a large deformation. So think about that cross section to be the wing, which is cruising at certain speed, which is creating these features. So this is just showing by changing the speed of the flow, what kind of interaction, structure, and you have. And this instability due to such interaction, so at a particular speed, so all the structures are defined for a given flight envelope. At a particular speed, you can have a instability, what we call dynamic instability, or flutter. These are some of the videos showing you the flutter. Military aircraft which has two wings fluttering. As you see in all these pictures, you will see this is a long span. This is anti-symmetric flutter. It's a typical tail flutter. This is a wind tunnel testing of the full-scale Boeing. In order to prove it, you need to do a full-scale testing to make sure that for different flow conditions, how structure responds. So, if you ask me why it happens that system has flexibility, inherent flexibility in it, and the vortices, when rated up due to a certain flight condition, has specific frequency, and those specific frequencies try to excite structure. And what happens that you think about it, the surrounding airflow will create a drag or damping. But in this case, it starts extracting energy from the surrounding airflow, and a specific mode. We'll talk about what is modes of specific modes of the wing get excited, and these things keep increasing time. The typical interaction, which is what we call mechanical resonance, happens on the wing. The most celebrated case, have you seen this? How many of you know about Tacoma Bridge? Okay, it's in 1940 in US Seattle. There was a suspension bridge, which was the first observed case of aeroelastic down. This came the elastic, when we mean elastic structure, it's a bridge. This is a nice video, the original video from the archives. This is a newsreel, so it will be interesting to see. I don't know you guys, how many of you have seen a newsreel in a theater? When we were growing up, typically before the movie, a newsreel will come, like a preview or trailer. Those days there used to be newsreel. So this is a newsreel of that way. So it will just, I found it to be.
Fatal day, and the wind begins to speak with a roar that no man can fail to hear. In a 40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you stood seeing as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saved himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. Here it goes! Engineers are divided as to the cause of the disaster. Some claim it was the use of...
You get the idea? I just like the video. I found it just a week ago. I thought maybe you guys will enjoy it. So this is the first case of a major case of aeroelastic, the disasters due to aeroelastic coupling. And the reason it happens because, like I said, flexibility in the structure. So have you guys learned a little bit of vibration? Anyone? Maybe in physics? You're a mechanical engineer?
Electrical. I'm mechanical.
So basically vibration means it's a motion which repeats itself in a specific interval of time. And there is a two scenario what we call an undamped system, which means the system oscillates forever. And then there is an underdamped system that oscillation starts and then it dies out. And why this happens, there is a physics behind it. Basically, if you look at the mass and spring and damper, so you have three main elements in any vibrating system. And this is associated with any flexible structure. Flexible structure will have some inertia, mass, which is related to the kinetic energy. It's the kinetic energy storing element. You have stiffness, like spring, how flexible a structure is, how compliant a structure is. That's related to the potential energy. And then you have the, so if there is a dissipation element, which can be external devices like dampers or friction or aerodynamics resistance. And this is what happens. You have, if there is no damping, basically kinetic energy converts into potential energy converts into kinetic energy, and this thing happens forever. If there is a damping, for each cycle, the energy is being dissipated to the system, and then the system stops from vibrating. So this, I just wanted to show you, this is a typical, whenever I talk about the aircraft structure, you just think about, okay, it has some mass, it has a flexibility, that's why it's moving. And it has some properties, some dissipation or energy dissipation elements. That's why it's dissipating energy. Ideally, if there is some dissipation, it will eventually stop. Any motion which will start eventually stop. However, there is a very unique phenomenon of resonance, which is the natural phenomenon of any structure. Any flexible structure will have what we call natural frequency or resonant frequency. The key thing about that, if you excite that system by its natural frequency, then the system amplitudes keep growing with time. You don't have to apply extra force. So it's very counterintuitive. Typically, you say that if I want to increase the amplitude of the motion, I need to apply more force. But if you find out a right frequency about which you start vibrating something, and it if happens to be its natural frequency, then you can excite its amplitude for a constant. And that is inherent to any structure you see around. Even you, if you stand in a shaker, you will have your own natural frequency. It depends upon the structures, stiffness, and inertia. Typically, that's what defines. And then if you incorporate damping, we call it damped natural frequency. The easiest example you can think about, swing. Have you seen the swing? Jhula. Yes? If you think about it, it's a kind of a pendulum. If you hold a person and let it go, and if you will realize that you don't have to apply a lot of force all the time. If you find its natural frequency and just tap it, it's that right frequency, that motion will exist. That's a easier way to understand one case of resonance. What I'm going to show you is a very recent case, and it can be a very expensive. Thank you. Have you heard? How many of you heard of Millennium Bridge? Anyone here? So this is a civil structure. This is in London. It's a pedestrian bridge which opened in 2000. Day of its opening, this is what happened. This whole bridge starts with lateral. This is what we call lock-in phenomenon. So because they have designed the bridges very well for its bending vibration, they assume when the people walk on it, most of the vibration will be downwards, perpendicular to the bridge surface. But because of the shape of the bridge, it so happens people start walking differently because bridge starts to move. So when bridge starts to move, people start to walk like this. And that happens to be the natural frequency of the bridge about which the people start to walk. And that natural frequency of the people motion, think about so many people walking at the same frequency, locked in with the natural frequency, lateral natural frequency of the bridge, and it created a large oscillation. So they need to redesign this bridge just within a week of opening, and it cost them quite a lot of money to analyze. So I'm just showing you that resonance, not only in aerospace structure, which you see in terms of flutter, where the wings are vibrating, the vortices excite the natural frequency or resonant frequency of one of the wings, which cause the dynamic resistance. So when we have to design and control what we call now active aeroservoelastic control, so we have an existing natural physical phenomena which is feedback loop. You need to design a controller on top of that. You need to find out what are the right measurements I have to do, and then what kind of control laws I have to use, and what kind of actuation we will do so that we can have a desired performance of the aircraft. And this combination of aeroelasticity and the control is typically known as aeroservoelastic. This is a good diagram which shows a different interaction. So in vibration, if you think about, we basically looked at the interaction between inertia, mass, and flexibility of the structure, elasticity. In aeroelasticity, we looked at the aerodynamics, elasticity, and the inertia of the structure. Aeroservoelastic, the combination. Then aeroservoelastic combines all this, which includes also the control, which is the C. So this gives you a general idea that as a mechanical engineer, I may just look at this portion. That's my area of interest. As a control, you may only look at this portion. An aerospace engineer may only look at this portion. And when you're designing the aeroservoelastic control, you need to have some expertise or some knowledge from different fields and try to put it together in a reasonable way so that we can have a successful experiment. And in particular, there are two types of aeroelastic phenomena or two types of instability. One is static instability, which is called divergence, and the other is called the dynamic instability, which is flutter. The static instability or divergence is directly related to how strong is your wing about its to carry a given moment or carry a torsional load. So it's very much related to torsional stiffness of the wing. And remember, whenever we are talking about wing, we have a structure which has its mechanical property, but on top of that, there are aerodynamics which changes the stiffness of the wing as you fly. When you're flying the aircraft. So at certain velocity, at certain speed, when the moment created by surrounding airflow overcomes the torsional, breaks the wing, that's called divergence speed. Flutter, the dynamic instability, that's why if you look at the divergence, it's like a buckling. Flutter, let me take it back, not buckling. Buckling has different types of oscillatory modes also. you can just think about exponential growth. Flutter is dynamic, the growth of oscillation as a function of time, and like I explained before, happens because it starts absorbing energy from the surrounding airflow, which is being excited, which has the vortices, which has frequency matching the natural frequency of the wind. And the whole idea is that when we are designing, we should avoid these type of flutter. Typically, flutter will happen before divergence. This is for any given design. First, you will have flutter and then divergence. So, since 1960s, people started working on to come up with an active flutter suppression strategy. It's not new. People have been trying. The very first success happened of the B-52 control configured vehicle. This is the actual aircraft. They used very fundamental classical control, used control surfaces. They have demonstrated that. If you think about it, this is its flight envelope, which is the predicted. And after that, it was predicted that it will flutter. And they have shown that from the prediction and actual, they got 10 knots. Knots is nautical miles per hour, around 1.7 kilometers per hour. They had got improvement of 10 miles per hour by applying the active control. So a wing which was supposed to only sustain at around 300, 30 or 40 kilonauts, knots, and it goes up to the right one. Remember, its flutter velocity also in the aircraft structure, you always have to think that its inertia, mass changes. Think about aircraft before the flight. It has is full of fuel. As you fly, it loses fuel, it changes its mass. So depending upon the overall load, which can include the mass of the fuel, aerodynamic load, for different load, there are different flutter speed, and you will see in both cases they have extended the or suppressed the flutter beyond that. The second success one on the F4 aircraft, they used 4 sensor, 4 accelerometer in particular in this case, and this was a collaboration between Wright Patterson Air Force Base, where I work, and the German company MBB, and they were using a classical tuning. PID or PD type of a control, where they were just starting with the fixed gain values and trying to see which gain value will work in achieving the flutter boundary. They have also shown the flutter. You can actively suppress the flutter. But this is a very very expensive and very risky adventure or venture, because you need to take the actual aircraft to its design limit and then hope that your controller works. So these were, like for example, the previous the B-52. These were the what we call marginally unstable flutter or weak flutter. So you just observe that, okay, my damping start to go down and down. Don't cross it. Don't go to zero, because as you go, damping goes to zero, your system has no damping and it will vibrate and break. So in these cases, they just go up till the flutter point and then they overestimated what will be. So there's you need a very good pilot to go up to that, push themselves to the flight envelope, make some readings in terms of vibration, and then design the control and test your control. So these were the 2 successful, which motivated a lot of subsequent investigation. What I'm showing you here is the typical flight envelope. So, and this is just a representation of flight envelope. There are different types of envelope. You'll see what you want to see, that it defines what is the velocity, what velocity. When you're ascending, cruising, and then you're coming back, landing. What is the envelope you need to maintain? Any civilian or military aircraft or design, at least you need to have 15% flutter margin. So if you have prediction that, okay, my this aircraft will fly maybe 100 knots. Then you need to, your maximum you can fly up to 85 knots. That's the maximum value you can have. In order to do that, we do a lot of over design. We do introduce a lot of redundancy in the aircraft structure. Whenever you are talking about over design and redundancies in aircraft structure, you are talking about making it heavier, making it less efficient. So there is a lot of interest that how can you design existing aircraft, or how can you modify existing aircraft which can fly beyond the boundary. You can increase the flight time. Or you have so many existing aircraft which has limits. Now you want to use active control, use the actuators which are the control surfaces on the aircraft, and can you make them fly beyond this flight limit? And when you're designing a new aircraft, what kind of design you do in terms of material, in terms of geometry of the wing, in terms of all the structural parameters, so that we have drones, for example, and fly much higher speed. These are, I'm not going to go into a lot of details. What I'm going to showing you, these are some of the very classic review papers. So if you really want to learn about the progress in aeroelastic control, these are the few of the review papers by Professor Livni, University of Washington. He has, I think he is the leading person in terms of aeroelastic control. This, he and the Carpel. These are the two people. So you will see that, and he summarizes what is the state of art of the active servoelastic control. So he's talking about the gust elevation system is already certified by FAA. It's installed in most of the aircraft nowadays. You see, aero servoelastic control for maneuvering has been successfully tested, and for some of the fighter aircraft it has been implemented. He's talking about the need for redesigning existing aircraft, and those papers you will find the details of a lot of other research in the area of active pressure suppression since 60s. And he is showing that there are a lot of academic papers happen, relatively small number of internal experiments, and very few full-scale experiments, because you can understand the expenses involved in these kind of testing. In AFRL where I work, these are the some of the primary programs in terms of aeroservoelastic control. They have an active aeroelastic wing program. So they want to concentrate on designing a wing of the aircraft which can be actively manipulated. And one of there will be HILDA, which is high lift over drag activating program. There are a lot of progress in this program has been highlighted in AIE reports. And I have given you some of the references which if you want to go into details, you can look into that. The good thing about these papers are they are not very technical in nature. They give you an overall idea what kind of a controller has been used, what worked and what did not work. These are the reports from the NASA or environment. So we can do the, they have shown that increased speeds and lightweight can be achieved for better fuel efficiency. GLA has been implemented. Swept wing, so instead of wing straight, you have a swept wing, and then they come up with the flow separator. There is a flow control problem. If you look at some of the Boeing, they will have nozzles at the trailing edge tip of the wing. Basically, they discharge the flow, the specific flow condition. They discharge corresponding flow to control the vortices behind them. An aerodynamic person can explain you better in terms of flow control. So there is a whole area where they are coming up how you can control those vortices by the fluids, by supplying the braking fluid, the fluids to technology. And the recent one which is still going on, this is the X56 by Lockheed Martin, and they have a they are called MUT unit. It's a that's being used for flutter separation and dust load elevation. These are the papers. If you're interested, you can look into those papers for more detail. So, as of today, these are the two current programs I know which work, or to some extent. For example, Boeing 753 active aeroelastic wing is used for dust load maneuver, so it can do that. It does not do the flutter control. However, the Lockheed Martin X56 has been designed test for active flutter control. And I believe in 2013, the first time they flew. 2015, it broke down completely during the test. Then again in 2017, for the first time, they have shown the body freedom. They can just control one mode. They are still working on it and redesigning the structure so that they can test that whether they can cancel wing vibration. It's a modular unit. One of the key feature about that you can change the number of control surfaces on the wing, and you can test different kind of single input, multi input, all kinds of controllers can be tested. And that's what I want to show you a video.
There is a dragon that lives in the air. It lurks where aerodynamics and structural dynamics collide. And it is called
I am not promoting Lockheed Martin. This is just a video which I found it. They explain their X56A program. Public domain.
Flutter is a result of aerodynamics forces and structural dynamics coupling and going unstable. Flutter can be catastrophic to bridges and aircraft alike. In 2005, Lockheed Martin initiated an independent research project to validate its flutter modeling techniques and to investigate the possibility of active flutter suppression. To minimize cost, 5 very lightweight expendable RPVs were designed and built. These vehicles were called Body Freedom Flutter Vehicles, or BFFs. The success of the active flutter suppression system demonstrated on the BFFs led to an AFRL contract to build and test 2 more. The MAD program was initiated by AFRL to mature active flutter suppression to allow longer, more flexible wings and lighter weight structures that'll allow future aircraft to fly higher, faster, and further than before. The X56A has been designed to perform other types of research as well. The X56A incorporates an open architecture vehicle management system computer, an expandable data acquisition system, air data flight test boom, 2 80-pound class JetCat small turbine engines with electrical power generation, excess power and volume for future testing, and a ballistic recovery system parachute to protect the valuable system during risky flight tests. The MAD program is delivering the X-56A MUT vehicle as a complete research system, which includes the ground control station, simulation, system integration lab capability, and a vehicle transportation and storage trailer.
Clear to test point 7.5. Roger, 7.5, increasing speed to 95 knots.
Now you can see starting to down to the body freedom cutter, and then they will turn off the controller.
Knock it off, knock it off. Okay, that verifies our flutter speed is 95 knots.
Flutter speed is 95 knots. Clear to test point 7.6. Flutter suppression on. Flutter suppression on. Cleared 7.6. Accelerating to 150 knots. 95 knots. 100 knots. 105 knots. 110 knots. 115 knots. 120 knots.
We are flutter free. I showed you 3 modes.
Don't think they have solved the problem. They have created a wing such that it won't flutter. You just have a body freedom flutter. They have come up with a wing design so that they don't encounter the other type of vibration, other parts of it. But they keep testing it and working on it. A lot of faculty, University of Michigan has a group which works on their data. One good thing about this, I believe in the recent version of MATLAB, they have provided the real experimental data coming from the sensor. So you can use them for system identification. So go to MATLAB and we are in the evening, try to look at the MATLAB help files. They have the model. If I remind me, I will post a link because it has the whole configuration of the wing. It has experimental data which they have done from the GVT ground vibration testing. And you can directly use to try some of your system identification tools which you have done during the course. Now these are some. This is the center I work on, where the mechanical engineers or aerodynamics, aerospace engineers, they are trying to come up with all kinds of exotic designs for next generation aircraft. The way we look at aircraft will be completely different in next 20 to 30 years. People are trying to understand what kind of a profile or the wingspan will be better. What kind of a control surface? Do we need to have a straight wing? Mathematically, those is no rational. We had the restriction of manufacturing capability. Nowadays, 3D metal printing or 3D printing is maturing. You can actually print the wings in any shape you want, which was previously not possible by any combination of materials. People are looking at those horizons and trying to come up with strategies. Profiles. These are based on the topology optimization to give the aircraft a very specific flight performance. I'm not putting a detail, it's taken from one of the paper. Need to put the reference. So when I say one of the goal is that you print wings, test it in the wind tunnel, put a controller on it, and check your control design. That's where we are heading to. This is one of my students doing a flutter testing of the given wings, which we printed in our lab. What you will see is that in the first video, so this is nothing but a rectangular wing made of the 3D printed components, and he is hitting with the hammer. So it is in front of a wind tunnel, which has air, which we can operate at different air speed. The first case, it is below flutter speed, the predicted flutter speed. And he will hit it with the hammer. We are doing a vibration testing on it. Think about the hammer, it has a gust hitting the wing. Then observe how it responds. And then we went near the flutter point.
Then once he hits, see how the response is. And then you will get a feel that it's a two scenario of aircraft flying at two different speeds. What will happen if a little turbulence or dust hit the You see, you hit it the same wing at that speed surrounding aerodynamic force of flow has enough damping that damp the wing oscillation very quickly. It was pre-flooded. And that's typically happen when it's surrounded by air, the structure has its own damping. But when you are near, so you have a sustained oscillation. Now, we have broken a couple of those. If you go more than that, it breaks very bad. So the idea I'm showing it with the new technology, which is much cheaper. If mechanical engineering department, for example, has a wind tunnel here, you can create your wing profile and do your test your controller, put some sensors on it, try to apply the controls you have learned. So there are things you can do at a smaller scale just to understand the problem, test your algorithms, the labs. There are a lot of experiments. I have done most of them with Dr. Cooper from University of Bristol and Dr. Motorshik from University of Liverpool. They have a big facilities for testing the aircraft, and they have shown. I will show you some of the results that how control, which I am talking about, the surface-based control, how it performs for now, in order to get the idea about what frequency we should be worrying about, we need to do testing. All the structures we see or which is approved has to have dynamic testing, ground vibration testing. These are the full-scale testing of spacecraft and component level testing of the aircraft. This is at the Cleveland where they do the ground vibration testing. They hang it like a pendulum. They have actually pushing it and let it fly. That will give you the body freedom flutter movement. They have embedded sensor all over the place. They, for a given input, they measure the response and from the frequency response function, they find out what are the natural frequencies, standing ratio, what are the modes which are needed to verify your model. This is one I use it in my vibration class also. This is an old helicopter. It's mounted on a shaker, and the shaker creates an excitation which corresponds to all kind of aerodynamic conditions. So it basically it is sweeping at different amplitude and frequencies and exciting this aircraft. Then it's embedded with a lot of sensors. So it's an old helicopter. They wanted to see that different amplitude and frequency of course influences different part of the helicopter what way. So they have just mounted in a shaker. Now what happens? They don't do it for all the helicopters. So I think I give you enough overview of the problem. So the rationale is that if you are designing an aircraft, redesigning existing aircraft, or designing a new aircraft, we want to have a flutter-free margin as a structural dynamics background. That's my interest. When you are looking at the next conceptual designs of next generation aircraft, we want them, it is coming up with all kind of sizes, all configuration of different type of control surfaces embedded in that. It is embedded with a lot of sensors. We want them to use at different altitudes, travel long distance at the high cruise speed. Hopefully I will come from US to India in 8 hours instead of 18 hours and perform in varying extreme conditions. So we will talk about we need to investigate not only traditional model-based control, but beyond that, data-driven control. One of the data-driven control I will talk, which is the method of acceptance. But at the end of the day, we need to, what are the data available to us? We have some time domain or frequency domain data coming from the real structures which we can use to design a controller. And we need to have certain actuator, but fortunately most of the aircrafts are already have a lot of control surfaces for different purposes. The idea is, can we oscillate the control surface and minimize the vibration? Because we have shown that we can do it in a lab scale, and we'll talk about how to do it by some of the small scale wing design. The other thing is that, which is an optimization problem, which we will not cover in this workshop, but think about it. The natural question to ask: if you are responsible for designing a wing, you need to ask yourself, where will I put a control surface? You need to understand its location and its performance as a function of its location. If you are going to use control surface as an actuator, then you need to understand its performance characteristics, how oscillates in that aerodynamic condition. What kind of actuator? Do you want to use hydraulic, piezoelectric? What kind of actuation system you will use? What should be the size of the control surface? More size can have more power, but at the same time it's surrounded by more aerodynamic loading. So there are a lot of inherently optimization problems built on top of the controller design. But once you understand the structure, people are working on the optimizing the structure. There are people working on the control, and if they come together, we can find a potential solution for the high-performing future aircraft. This is in particular my research, what we have done so far, and what are the red ones, what we are investigating. We want to design a controller purely based on acceptance transfer function, which can be available from the experiment, from the model, or in flight data. We want to extend the flutter boundary. We have shown that in principle we can do it. We want to come up with one control gain for the entire flight envelope, so that you turn on the controller and then you will be safe. For the extended flutter boundary, we can do some partial pole assignment or targeted flutter mode, and I will talk about it one of the lecture, the concept and its utilization. And the coupled system is actually one of the areas where the partial pole assignments can be successful, if we understand. We need to come up with what should be, how much amount of energy we need to drive those control surfaces. So one of my students who just graduated investigated the effect of sizing and location of control surface on aeroelastic control. The student who is working with me, she is investigating the type actuator which will have minimum power requirement or minimum heat generation if we want to achieve the same flutter boundary extension using that. With this is the overview of this course, and I will start in the afternoon after we are back from the lunch. I will start with a very simple structural dynamics overview and a little bit of PID. It will be trivial for most of you because you are a graduate student, PhD student, but some of the undergrad students. But I am trying to bring the physical insight from the mechanical engineering side. You have seen those maths. Hopefully, you will understand true meaning of when we talk about eigenvalues of force in mechanical engineers, what we get. So that will be a more simplified version, second half, which I treat it to be a refresher for you. Then tomorrow we'll talk about the feedback control and then receptance control, aeroelastic control. This is the structure I have planned so far. I am receptive to any feedback you have. No active feedback loop. Give me feedback. I can to bring some activities which can help you out. So I am open to any kind of suggestion you have. Any question or comments for this overview? Do you guys want to work on MATLAB problems? during that workshop. You bring your computers. That's what I'm assuming. They're bringing their own computer. You can work in group. For this end of the course, there will be 1 hour in-class exam, and one I will give them take home. Yeah, just one wing model I will give you, and then on that you can show a state space control, the new control which I have taught you. If you can recreate those, the results of technical paper, I think you can then, you have, as an electrical engineer, you have been exposed to a lot of fancy controllers, LMI, adaptive. But what are the other controllers you guys? What are the other control ports you have? Sliding mode control. So you can try those small wing models, okay? And of course, I will talk about reception-based control, which is my area. You need to talk to me, otherwise I will feel sleepy after some time.
Okay. Resume and clear from. Come with your laptop.
No, today is no workshop.
No laptop.
Today is the, I mean, they can bring, you know what? If you want, just bring a MATLAB and we'll see. You can do something on MATLAB. I can start with MATLAB. But I wanted to just give them a review of structural dynamics. Tomorrow they have the discussion. Now, why don't somebody can make a Google Drive? You have the list of students. Can you just make a Google Drive so that I can post codes or handouts, additional handouts of this lecture, so that you have everything. We are working on a problem.
Create a Google Drive. Kitangar has all the mail ID. Not mail ID. I will give you. It's not mail ID.
Nikhil, talk to me. Yeah. Don't hesitate.
Sorry, told about a bridge.
Yeah.
Natural frequency, the which due to the difference creating, the natural frequency of the bridge is vibrating. Now, if we want to control that particular vibration so that the bridge doesn't break down, or it is a flight, or maybe it's a helicopter that is showed in the previous slide. So, how will we choose the particular frequency array so that we can restrict the vibration for a flutter eventually? So,